Hi guys, welcome to Acharya's Learning. Today our topic is glomerular filtrations. We're going to discuss about the process of urinary formations, okay? So let's start with the basic concept here. So whenever we talk about the glomerular filtrations, we're basically talking about the urine formations. So the urine formations are a result of three different processes, and that's what we're going to talk about today, okay? So usually the urine formations are a result of like a couple of things, okay? Let me write it down that way. So what are those, the steps are, one is called, okay, let's say the urine formations, okay? So urine formations are a result of three things, okay? One is the glomerular filtration. So we'll write down, okay, you have a glomerular filtration, okay? That's something that we're going to talk today, okay? But not only urine formation depends on the glomerular filtration. As I said, it depends on three different processes, right? One is glomerular filtrations, and other one is going to be, I'm going to write it down. 1, 2, and I'm going to write 3 here. Other one is going to be your tubular reabsorption. Okay? And then third one is going to be your tubular secretions. And we'll talk about what this each means, okay? But as we go, you'll get to understand more about it, okay? But let me tell you guys that this is like one of the most important discussion that we're having today, okay? Glomerular filtrations. So it's really important that we have a great understanding of this, okay? So as you come back here, okay, like I'm going to quickly talk about the structures. I've already done this, so if you haven't watched the structures of glomerular structures, I would recommend you to watch that first and then come back to this, all right? So if you see here, like what I did is I draw this heart, and then this is going to be my what? That's going to be my pulmonary trunk and the pulmonary artery, right? And then I also draw this left atrium, left ventricle, and then the aorta, okay? This is a descending aorta. And then remember, from the left ventricles, from the aorta, that gives rise to systemic circulation, right? And today we're talking about the renal. So basically, if you come back here, okay, I drew one renal artery, okay? This one is going to be my, let's make this as my renal artery, okay? This is going to be my renal artery, all right? And then it's give branches to like different things, okay? We have already talked about this. I'm not going to go super detailed about this. But this one I do here, this is called efferent, okay? I'll just read. This is called efferent, okay? Arterioles, all right? And you can remember these as A for like arrival, okay? It's arriving or bringing of blood to this capillaries, okay? This is now tuft, a network of capillaries. We call them as glomerular capillaries, right? And from the glomerulus capillaries, these blood vessels coming out, this is called efferent arterioles, okay? So this is going to be my efferent arterioles. And then efferent arterioles breaks down into these capillaries, which is going to be my peritubular capillaries, okay? And all these things, the reason why they're called peri is because it's actually pairing, it's actually sort of like around this, all this tubular, these tubes, okay? So because of that, they call it peritubular capillary. So all these things are peritubular capillaries, and all the way down here, that's going to become later, the peritubular capillary is going to become your venules and veins, right? And ultimately, it's going to turn into inferior vena cava. So this red, I drew as the peritubular capillaries from here to all the way down there, okay? Now, so this is my glomerular structures, okay? And this, you see in the blue right here, that is going to be my basement membrane, okay? A glomerular basement membrane, all right? And where I talked about that too. So I'm not going to maybe like quickly label this one for you guys too, okay? So this is going to be my glomerular basement membrane right here, okay? And this, you see this in a black, these are my podocytes, okay? And this right here, these are the food process of my podocytes, okay? And then we already discussed about the role of this one too, okay? Now, these are three different membranes, okay? So whatever substance that gets filtered out from here, it has to pass through all this barrier to come down here on this Bowman capsules, okay? So if you see from here, like this, from orange here, that is going to be my Bowman capsules right here. So all the way these structures, okay, like a cup substructure right here. This is Bowman's space, right? And this one right here, this structure is my proximal convoluted tubule, okay? And this is going to be this structure right here. It's going to be my descending, okay? It's a descending limb, okay? And this is going to be my loop of Henle right here, okay? And this is my thin part of ascending limb. This is going to be my thick ascending, okay, I'll just write down ascending limb, okay? Or you can say proximal convoluted tubule. This is a descending part of the loop of Henle. This is ascending part of the loop of Henle. And you see in this one, this is going to be my distal convoluted tubule right here. And then this will get drained into what? The collecting duct, we'll say. There are different types of collecting ducts. So like, there is like if it's a cortex, we call them a cortical collecting tubules, okay? And if there is in medulla, we call them inner medulla collecting tubule. And then later we have outer medullary collecting tubule too. And then later, what comes out here is the urine, okay? And this will, from here, the urine will go drain into something called renal papillae. Then after that, it will go into minor calyx, then major calyx, then renal pelvis. Then from the renal, it's going to go to ureter, and then it's going to go to bladder and urethra, and then it will come out, right? That's usually, it will happen. Okay? And this is like one nephron that I drew. But guys, remember this. There are going to be millions of nephrons. Each kidney has about like 1 to 1.2 million nephrons, right? So if you have 2 kidneys, then you're going to have about like more than 2 million nephrons, okay? I just drew one nephron in here. But one more thing I do want to emphasize that your kidney, if you see it around here, right? If you draw just one nephron, then your one nephron is sort of like drawn in a series circuit, okay? So what is it? It is more in, if you talk about just one nephron, okay? Let's just write down one nephron, okay? If you talk about one nephron, it is on what? It is on series circuit, okay? It is on my series circuit, okay? But usually if you're talking about, let's say, if you're talking about all the nephrons in your kidney, then they are going to be in parallel fashion, okay? The parallel circuit, okay? But I'm just talking about one nephrons right here, okay? And then if you look at the one vasculature, these are more, one series, okay? But if I talk about other nephrons, like, okay, because there are millions of nephrons, then it will be more of this. So it will more arranged in a parallel circuit, okay? And that is something that we have to talk about because of the resistance, okay? Because the kidney, if you're not talking about one nephrons, if you're talking about the millions of nephrons, if you talk about all those nephrons, then what happens is that the glomerular filtration rate differs or the resistance differs because they are aligned in a parallel fashions, okay? I do want to emphasize on that too, okay? Now, after this, as I said, okay, that urine formation are a result of 3 different processes, One is the glomerular filtration, whatever that's filtering out here and going to Bowman's space. And then from here, proximal convoluted tubule, from all this part, ascending limb, the reabsorption happens. All those substances that got filter out, they get reabsorbed. But at the same time, secretions also happens from the peritubular capillaries, okay? So, urine formation, that's why we say the urine formation result of 3 different processes, okay? But today, we're only focusing on this glomerular filtration. That's what we're going to talk about. In other lectures, we're going to talk about the tubular reabsorptions and also like tubular secretions, okay? But today, we're going to emphasize only on the glomerular filtrations, okay? Now, if you come back here, all right, so what we're going to do is that if we talk about this, okay, so whenever we talk about glomerular filtrations, okay, one thing that we have to talk about is something called glomerular filtration rate, okay? What does that mean? I have to define that, okay? You probably have heard this a lot. This is called glomerular filtration rate. And what this means is that the glomerular filtration basically is that the amount of plasma that gets filtered out from the glomerulus, okay, filtered glomerulus per unit time, because whenever we talk about the rate, we are talking about the time, okay? So that's what it means. But before even we go and talk about this, let's talk about this thing. Okay, what is coming from here? From the aorta, blood is coming out here, right? So whenever we talk about the blood, a couple of things that we talk about. So what is blood is composed of? Let's talk about this. So this is blood, and what is coming here in the renal artery is coming out. So we call them a renal, okay, blood flow. Okay, so whenever we talk about renal blood flow, okay, what does the blood consist of? Blood consists of a couple of things. Okay, so we have to talk about blood consists of, let's say, okay, if I quickly draw this diagram right here, okay, follow me. If I do this, let's say if I centrifuge it, okay, if I centrifuge it, what do you see? You see that about, let's say from it varies from person to person, okay? But if you centrifuge it, then you see down here something called hematocrit or packed cell volume, okay? And that's probably about, like, for our case, I'll say 40%. For men and female, the difference is usually from 37 to 45% or so. That's usually hematocrit, right? And also, like here, a little bit, you see this here. This is called buffy-coat, and it's about 1%, okay? Which contains like your white blood cells, you know, your platelets, okay? And then after that, you have to see this right here, all the way down here, all the way this one. This is going to be my plasma, okay? So, you're talking about these things, okay? So your renal blood flow, and the blood contains your cells, your red blood cells, white blood cells, and your platelets. Those are formed elements of the cells. And they also contain plasma, right? So, that's what we have to talk about. And you can think about this one as that the renal blood flow is coming down here, and they consist of all of that, okay? Because this glomerular filtrations apparatus, you can say, you know, they're kind of like, you can think about, they're kind of like a centrifuge, okay? Because what happens is that they can only allow the plasma to get filtered out. Red blood cells, white blood cells, and platelets, they cannot get filtered out because of their size, okay? Because they're bigger size molecules, okay? Because they're bigger cells. So because of that, they do not get filtered out. So only what gets filtered out is your plasma, okay? That's the reason why we have to talk about the plasma, all right? And then, guys, if you know, what is plasma? Let's quickly talk about what does plasma consist of, okay? Let's talk about that. Your plasma consists of what? 90 to 90% time it consists of water, right? Then it has sodiums, right? Then it has magnesiums, all these electrolytes. It has chloride, right? It has what? Sodium, magnesium, chloride. You have a calcium ion, right? You have a potassiums there, right? They have all this. Now they have bicarb there, okay? What else is there? These are your solids, right? But they have also metabolites, like for instance, you have a glucose, right? You have a glucose, you have amino acids, right? Because these are all things that get filtered. I'm just writing it down, right? Glucose, amino acids, lipids, okay? Even some like ketone bodies, all right? And what about any sort of like a metabolic waste? Like for instance, metabolic waste like urea, okay? Creatinine. They also get. What about some of the hormones like insulin? Okay, myoglobin. Okay, and what about other known substances? Like for example, we'll talk about this too. There are something called inulin. Okay, or PAH. Okay, this stuff. These are protein, right? The insulin, myoglobins are proteins, right? They do get filtered out too. We'll talk about this, okay? So now, these are like solids. You have lipids and some of the hormones, right? Even like, you know, you can see like some of the T3, like T3 also can get, T3, T4 can also get filtered out, but very less amount, okay? But anyways, so usually these are the substances that is filtering out all the time, okay, from the kidney, from there. So usually the plasma consists of all that kind of stuff. But remember, plasma also consists of what? We haven't talked about it. Like for instance, like bigger molecules, like one of the main one is what? Your albumin, right? We have to talk about that too. Your albumin, okay? And then like there are fibrinogen, okay? And then also globulins. Okay, and these albumins and fibrinogens, and they're the larger molecules, okay, so they usually don't filter out, okay. Albumin could filter out, but because of the negative charges from here, based on membranes, they do not get filtered out, alright. So that's something that we have to talk about that too. But anyways, in general, these usually about like out of the plasma, about 90 to 92% is going to be about your water, okay, in plasma. And then about like 7 to 8% is going to be your proteins, those albumin, and then you have your globulins and your fibrinogen, right? And other this like 1% or so will be the solutes, electrolytes, glucose, amino acids, lipids, ketone bodies, fats, urea, creatine, potassium, calcium, all that would be there, okay? But now, so this is generally what your blood consists of, right? I mean, your, let's say, plasma, blood altogether, that's your blood composed of, right? Now, so whatever we do, let's say, that means if I could put that in equations, and if you come back here, so I could just say renal blood flow is equal to what my renal plasma flow over, I have to do 1, because this is how 1 came in, because it's Buffy code, 1 minus my hematocrit, okay, or my packed cell volume, okay? So in that case, let's I want to figure out how much plasma is coming out here, right? Okay, because remember, your cardiac output is what? Your stroke volume times heart rate, right? And cardiac output is about like 5,000 milliliters per minute, right? That's what happening. And about 20 to 25% of that 5,000 ml, okay, your kidney gets about 20 to 25%. So let's just say for our case, we'll say 20% it gets, right? Out of those 5 liters or 5,000 ml per minute, right? So if we get that, let's say renal blood flow is what? We said it's going to get about 1,000 ml per minute, right? And then we're trying to find the renal plasma flow, which is, we do not know that. And then you do 1 minus, you do hematocrit percent, and simply say, we said 40%, so that would be 0.40, right? So if I do this, multiply that, your 1,000 ml per minute over, if I do this renal plasma flow over 1 minus 0.4, that would be, what is this? 40, that should be about 0.60. Okay, and if you multiply this 0.6 times, okay, over 1000 ml, what is that going to, that's going to give you my 600 ml per minute. And what is this? That's my renal plasma flow. You see what I mean? So that means if my renal plasma flow is 600 ml, what is going to be my hematocrit, or let's say cells that consist of, that would be, if it's 1000, I could just subtract 1000 minus the 600, so that should be able to give me like 400 ml, okay? So let's just write it down here. In here we're writing these things down, that you have let's say, you have in the red blood, okay, your renal blood flow consists of what? You have 400 ml of cells, okay? And then you have 600 ml of what? Per minute is your plasma. That's my plasma, okay? This is the plasma that is going to get excreted out. And remember what we said? Plasma consists of all of that, right? Okay, now, that's what is happening here, right? So those water, sodium, magnesium, chloride, all of that is going to get filtered out, right? And one more thing is that, as you know that, these guys are unique, in their own ways, right? Because these guys have these endothelial cells right here, right? And they have this porous, right? They're highly porous. That's why we call them fenestrated capillaries. They have a glycocalyx and all that kind of stuff too, right? And then they have this basement membrane. And glomerular basement membrane is heavily negatively charged. Okay, because they have all this like heparin sulfates or collagen 4, right? They have this laminin 11, fibronactins. Okay, these are all this like siloglycoproteins we call them. They're heavily negatively charged. So because of that, what happens is that any molecules that are negative, let's say anionic, okay, they have a little more difficulty to filtering through when comparing the positively charges, okay? Like for instance, if it's sodium versus, let's say, chloride, okay, sodium can easily pass through much more better versus the chloride, because chloride is negatively charged, okay? Still pass through, but it has a little difficulty get through it, okay? That's right. And these are what? And then I also have this guy, which is going to be my podocytes right here, right? And these podocytes have this called what? These are my filtration slits, okay? And this is what I'm drawing is nephrin, okay? This is a protein, okay? This makes your filtration slit diaphragm, okay? This nephrins, it's a protein that makes a filtration slit diaphragm. Because remember, if there is a mutations on this genes, your nephron, you can get a pathological conditions, okay? They call this Finnish type of congenital glomerulonephritis. You can get that, all right? And these are hanged by the porosins, okay? And then there's also anchoring, like alpha-actinin 4 and that kind of stuff too. But one more thing I do want to mention is that, actually, I'll mention that later. But what we're going to do is that whenever we talk about this one, right, we have to talk about this in what ways, how the filtration is occurring, okay? Whenever filtration to occur, something has to happen. Some kind of forces needs to be here in order for any filtration to occur, okay? And we have to talk about those forces. And those all the forces that is contributing to having these filtrations to occur, glomerular filtrations, those forces are described by this thing called Starling forces, okay? This is Starling forces that we have to talk about. And remember, whenever there's a pressure involved, we're talking about mechanical forces, okay? So there's a mechanical forces here that's driving to have this filtration to occur. And that's what we're talking about, okay? Now, what are those forces, okay? And because we're talking about the glomerulus, we're doing the glomerular filtrations, and it's also, we're talking about the time, because remember, this is coming, 600 ml is coming, and as we said, the blood does not filter out, but the plasma can filter out, right? The plasma is the one that filters out. But the plasma to filter out, what happens? There has to be some kind of forces, okay? So that glomerular filtration rate, the glomerular is this, filtration is happening on the time, it depends on a couple of things, okay? And we will talk about that. What are those? Okay, let me erase this, alright? So now, your glomerular filtration rate primarily depends on two things. And what are those things? That is called, okay, it's called effective filtration pressure. Let me just write down. Effective, okay, filtration pressure, okay, and then also your filtration coefficient. Okay, they say this as a K. This effective filtrations, okay? And what is effective filtration pressure? You probably are used to hearing about so-called net filtration pressure, you can say, call that. Or there's also another, which is called pressure, okay, ultrafiltration. You can simply call that also. So your glomerular filtration rate, which is basically means the plasma that is excreting out by all the nephrons per unit time, that is defined as glomerular filtration rate, okay? And this glomerular filtration rate, it depends on two things. One is called net filtration pressure or effective filtration pressures, or you can say pressures of ultrafiltrate, and then also filtration coefficient. That's what we're talking about, okay? And these are mechanical forces. These are the forces that's driving for the filtration to occur, okay? Because there has to be some kind of pressure for any sort of like a concentration to get pushed down from here to get into this one, okay? So that's what we're going to talk about, the forces right here. Now, so those forces are usually, so let's just talk about, this effective filtration pressure and then also the filtration coefficient, okay? So usually what happens is that, let's say now this plasma is here, okay? This plasma is here, and the plasma is here, okay? This plasma consists of water right here, okay? Magnesium, you have a calcium, right? And then you have, what is this? Sodium, bicarb, lipids, right? Ketone bodies, okay? All those like myoglobin. You have insulin, right? You have those hormones too, right? So all that kind of stuff. And obviously we cannot forget glucose, amino acids, all of that, okay? All these things are actually going to get dumped down here, okay? And then somehow this tube has to reabsorb that, because remember, these are highly porous. The diameter is about, for the endothelial cells, is about like 70 to 90 nanometers or so, right? So all this can filter out. And also remember, this one is this. So all these things, in order to get filtered out, this depends on two things, as I said. One is the effective filtration pressures, and other one is your filtration coefficient, right? And what is filtration coefficient? Let's talk about this one, and we'll talk about the effective filtration coefficient. This filtration coefficient, which basically means is that this filtration coefficient itself depends on two things, okay? One is called, okay, we'll write it down. It's called surface area, okay? Okay, and then other thing is called, so-called, you have a hydraulic conductance, okay? And which basically means is that, this basically means is the permeability we're talking about. We're talking about the permeability, okay? Because remember, if you remember the rate of diffusion is equal to, by the Fick's law, okay? What did he say? Rate of diffusion is equal to, because it has to get diffused through, right? Is equal to, you have to do pressure, okay? Okay? Times, which is this pressure that we're going to talk about, times, you're talking about the area, the surface area, times, okay, this one, which is what? This small d over the thickness. Okay? That's what he meant by, right? And these small d's represent as what? Diffusion coefficient. Okay, that's what it means. Which itself depends on what? That itself depends on a permeability, okay, over the square root of the molecular weight. Okay, that's what it is. Because remember, this pressure talking about the pressure gradients between here and here, okay, the glomerulus and the bowman space right here, and then the area means, like, if you have a larger surface area, what's going to happen is that you're going to, it's probably going to be, your rate of diffusion will be better, right? Because your rate of diffusion is directly proportional to the surface area. The higher the surface area, diffusion will be better. Okay, the better would be the better it will get filtered out. Let's go with that. And then your diffusion coefficient is equal to permeability over the square root of molecular weight. Because remember, this, whenever we're talking about molecular weight or molar mass or delta, we're talking about the size, okay? If the larger size, like for example, let's say globulins or larger molecules, okay, like peptide proteins, they would not able to filter out because they are large in size, okay? Large in size. So that's the reason why the permeability is inversely proportional to your molecular weight. Like for example, let's just quickly talk about, do you guys remember what is the molecular weight of, let's compare a couple of things. What is the molecular weight of sodium? Might have to go back to the high school chemistry here. Sodium molecular weight is about, I think, about 22.9, right? Dalton, DA, or you can say, because remember, 1 DA is equal to 1 gram of like millimole, right? That's what it means. So this is 1 gram over millimole. So my mic is coming off. Okay, so 1 gram, so that's what it is. And then if you know, for example, let's say we will say your potassium. What is potassium? Potassium is what? About like 39 point something, right? Your potassium is that, your sodium is this, right? And if you talk about calcium, is about like 40 something, right? 40 Dalton. And if you see water, what is the water molecular weight? That is going to be, if you know oxygen is 16, right? On the 2, that would be like about 18.01, something like that, right? And then if you know the glucose is what? C6H12O6. So 16, this would give me about like 180, right? 180 DA. Okay, and then if you remember the magnesium is what? About like 24, right? That's a molecular weight. So if you compare this, look at this. Sodium is 23.9. Okay, and if you look at the, let's say the chloride is about like I don't know, like about 35 point something. Chloride is going to be, yeah, chloride is about like 35.45, I think. That's a Dalton, right? So if you look at this, if you compare that, your sodium molecular weight is really important, because the smaller the molecular weight, okay, the more the permeability would be higher, okay? That's why I just wanted to lay in the comparisons. And also remember, the water freely filters out from here, okay? That's why we're talking about the hydrolytic conductance, okay? Usually water is excessive on the water can easily filter out, because remember, look at the water molecular weight. It's like 18.01. It's less than even sodium, okay? So water like freely filters out from here, okay? And I'm just giving you this so you can look at the molecular weight and then compare, okay? The smaller the molecules, the higher the permeability is, okay? That's what it is. And other one is your surface area. If you have a higher surface, let's just make it. Let's make this one. If I say this is my blood vessels, okay, and then my another blood vessel is, let's make this as this one, okay, and this is, let's say this is my channel, it's flowing down, okay, and let's make this one channels. So these are like a porous, like a fenestrated pores. So if which is going to have a higher glomerular filtration, right? Which is from this one, right? Because there's an increase in surface area, right? So because there's a lot of surface area, a lot of pores there, a lot of fenestration there, a lot more can filter out from here because there's an increase in surface area. And the permeability is like these sizes, okay? If I make the sizes, let's say bigger down here, what is going to happen? They're more permeable to filter through substances. So that's why this filtration coefficient is directly proportional to your surface area and the hydrolytic conductance, okay? Anything that can destroy surface area or the permeability can affect your filtration coefficient, and if that filtration coefficient get affected, your glomerular filtration rate will get affected, okay? But remember, filtration coefficient is one of the thing is that filtration coefficient does not change day-to-day basis, okay? It has to take a lot of times for the surface area or even the hydrolytic conductance to be disturbed, okay? And some of the conditions, like I think if I quickly mention, there's two of them, I'll mention this. If you want to mention, usually it's like a diabetes or even hypertensions, okay? They can create problems into this. For instance, you know, with the diabetes people, a lot of glucose are attached here, right? A lot of glucose will be here, and when the glucose gets accumulated, what happens is that those glucose will start attaching on the surface area, okay? And they'll make restrictive, okay? And the lipids and all those protein will also get deposited around down here. So then what's going to happen is that's going to damage this glomerular apparatus, this filtering membrane, okay? So that's going to disturb that, but that happens over the years, okay? Even the hypertension, because of the higher pressure, okay? Initially there will be increase in GFR, but continuously having a higher pressure, what's going to do is that's going to cause a problem in here on the permeability, okay? And it also damages the surface area over the times, okay? So in that case, the filtration coefficient will change, and if the filtration coefficient will change, your GFR is going to change, okay? But as I said, this does not, the filtration coefficient does not change in a daily basis. There has to be conditions, and it takes over the period of time, longer period of time, for them to have any sort of changes, okay? What does changes in a daily basis is this guy right here, the effective filtration percent. We'll talk about it, okay? So quickly, if I want to talk about this, let's say filtration coefficient. Your filtration coefficient has an equations too, okay? Your filtration coefficient is directly proportional to your glomerular filtration rate over your net filtrations or your effective filtration pressure, okay? That's what it is. So if I want to find, let's say quickly, if I want to find your filtration coefficient, right? How do I find? I just have to do, okay, my filtration coefficient is equal to, I have to know what is my GFR, okay? So we will not talk about it. Usually what happens is that out of the 600 ml per minute, about like 20% gets filtered out, okay? If he gets 20% of 600 ml, how much is that? That's like 20%, so that's 0.22. That would be about 120 ml per minute. Okay, that's what is happening. Okay, and effective filtration pressure, you'll know what I'm talking about, but usually it's about like 10. Okay, so when I do this, okay, 10 millimeters of mercury. When I do this, your filtration coefficient is equal to 12 ml per millimeters of mercury per minute. Okay, this is my filtration coefficient. But this 12 is telling me about, because remember, if my GFR is 120 ml per minute, this 120 ml per minute is representing not one nephron. It's representing for all the kidney. Like, sorry, not all the kidney. 2 kidneys, all the nephrons, all those 2 million nephrons I'm talking about. That is this filtrations of those, both the 2 kidneys, okay? This is what this both of them. And out of this, about 119, what happens? 119 will get reabsorbed, okay? And then about 1 ml will go to the urine. Okay, this would be the urine. Remember one more thing though. Whatever your excretion is the urine. This excretion plus the 190 that gets into the renal veins, and then it will go to the inferior vena cava, okay? Whenever you add the whatever amount concentrates in the renal vein, okay, plus the urine, that has to be equal to the plasma, okay? So remember, 120 ml got filtered out, right? That has to be equal to the, okay, that has to be equal to the, this one, which is 1 ml, which is the excretions or urine, plus the what drained into inferior vena cava, okay? That has to be equal. So that's how they maintain the homeostatic, okay? So that's something that I wanted to quickly emphasize on that too. And this is the filtration coefficient, which basically means in this 12 ml per millimeters mercury per minute for this 2 kidney, in this one, this is basically representing the hydrolytic conductance and the surface area of those two kidneys. Okay, that's what it means.